Our second
you.
speaker is Juncai from UT Austin in the Department of Mathematics. He's going to talk about approximation properties of deep learning CNNs. Let's welcome.
Okay, yeah. Thanks so much for organizers for such a wonderful workshop. I'm really appreciative for the chance, for the opportunity to present our recent work about the approximation properties of deep ReLU CNNs. This is a joint work with Professor Juncai from Penn State and Nini from Peking University. Okay, so yeah, Shuha just give a great presentation about how to apply transform in solving PDEs. Transform is very popular and fancy today. So today I will talk about some old fashioned things about the still about the application of science in programs. So let's start our story from a more from an older fashion, that is about the classical CNN structure. It's about, for example, the Net5 is the first, which is considered as the first successful convolutional neural network, like for digital number. And also this AnnexNet, this is considered as the beginning of the new revolution of deep learning. We are coming from the background of computational mathematics. So there are some perspectives from computational mathematics to try to understand and try to improve this science. For example, the dynamic system viewpoint, which is very, very popular recently, I believe. And also we propose to use multi-grid or iterative method to understand also for the reasoning type of science. But there's questions like, when we start DNA, the first thing is about approximation, but when we start saying it seems that like here, and there were very few studies about to deal with the approximation properties of science. And so there are like people don't believe science can have approximation ability, or it seems that people don't believe that we need approximation for science. But in some situation, we actually need, for example, like recently we noticed that science is more and more popular in like numerical PDEs and scientific computing, right? Especially like also the similar case like what Shu Hao mentioned, like for inverse program, if you have an input as like some observation of your solution, and you hope your output is like the source term. And if you have a structure grid, and then this map is from like almost from a matrix to a matrix, right? When you talk about a matrix to mapping from matrix to matrix, right? Science becomes a natural choice, right? Also before transformer. Okay, so in this kind of situation, approximation theory becomes necessary for CNN. Okay. So here we start. We first try to like to show that okay, the approximation theory for classical structure of CNN. Then we try to extend this kind of result to a more popular or architecture like a ReSNet, pre-arch ReSNet, or ImageNet. Okay, so let's first have a setup for like for notation. We follow the notation in PyTorch. We think about our input. It's almost like, okay, you have C channel, and the spatial dimension is like D times D. You can think about the, for example, say equal to 1 for grayscale image, or say equal to 3 for color image, or say equal to 1 like for if you want to reconstruct the mapping from the solution to your source term, then this U is this X is a solution on this is a solution of PDE on structure grid. Okay. And you think about it, you have a kernel with the input channel, lowercase c, and the output channel, uppercase c, and the spatial dimension for this kernel is 2k plus 1 times 2k plus 1. This k can be actually large, but finally, our main task is like to reduce this to 3 by 3, right? Okay, so then we define this convolution with multi-channel as like this. Then you will notice that right here, this index will exceed the range of the dimension 1, 2D. So we needed to pad. Here we introduced two mainly use the padding. One is constant padding, which means you pad a constant around your input, or you can do periodic padding, which means that you pad your input to be like a periodic function, like from each dimension. And then we have this classical deep ReLU CNNs. Here we assume that the sigma stands for a ReLU function, and we will explain later why this can only works for ReLU activation. And here, then we have this CNN. Right? CNN is a special kind of DNN, which means that we just replace the fully connected layer by convolution layer. And here, and because of a parameter sharing, we have a special form of bias. And then after all, you will got a third order tensor. Then you vectorize it. You put it as a vector, and then you have this last phylon linear layer. And here we mentioned that in practice, right? In practice, we only apply convolution kernels with 3x3 kernel with multi-channel. And here this will stand for like a vectorization, and this B is like to denote the bias. Okay, we first show the approximation for classical things. Think about you have omega. This is a bounded domain in this like a matrix space, but this is just you think about you vectorize your matrix as a very high dimensional vector space, and you assume that this function is like have a barren norm is bounded. Okay, this barren norm of this function is bounded in some sense, and then we prove that there exists a CNN with as defined before. Okay, with 3x3 kernels, multi-channel. Here we give some this hyper parameters of this CNN, which means we have the depth that only depends on the input dimension. Okay, and we have the width, like the number of the channel, also only depends on the the dimension of input. And here, this output channel for the last convolutional layer, that only depends, that can be arbitrarily large. That will characterize the approximation power of a CNN. That is, okay, look at this order. I guess if you're very familiar with this kind of like approximation server of DNN with one hidden layer to deal with like under a setup of like a barren space setup, we're very familiar with this kind of order, right? So here, then we will we have some properties of this result. Okay, this is for 2D. Okay, which means that right, if you deal with 2D image processing or 2D like numerical PDEs, you can, in some sense, you can may apply this theorem. And here, this result is only for like, okay, which means that it seems like you have just one channel, but actually this can be applied to a multi-channel case. That's that also work. Okay, and this convolution here, like before this KL, this convolution is considered as the most commonly used type, right? If we use raised net, dense net, efficient net, or then we just use this 3x3 kernel with multi-channel with a constant padding or periodic padding. Here, one thing I want to mention is that this cannot be applied to a reflection or replication padding. I will show it later because of the important thing. Okay. One thing I also want to mention is that this result, right? You will say because this CL, this CL only depends on the dimension of input. So as asymptotically, we achieve this the same approximation rate to this DN with one hidden layer, and we believe that this can overcome the curse of dimensionality because for a 2D input, this D square, if you say this is an essential dimension, right, that will be extremely large. So, but anyway, you can always keep this half order of your approximation power. And we will show it later. This can be applied to ResNet, pre-act ResNet, and MGNet. So here we put some remarks about the result. Okay, first, actually we can just use 3 steps to prove this theorem. One is like you have we can establish a connection between DNN with one hidden layer and the CNN with one hidden layer, but you have an extremely large kernel. So right, this is not commonly used in practical setting, and so we need the following theorem to this is a decomposition theorem for convolution with large kernel. This K can be arbitrarily large. This M is almost like the channel of output. So you can have a series of a small 3x3 kernel. This is a linear result, but this is a pure algebraic and constructive result. And this result only works for constant and periodic padding, does not work for reflection or replication padding. And then you have this result, you just need to rewrite your CNN with one hidden layer with large kernel as a deep CNN, right, with 3x3 kernel. But here you need to put the activation function. So here you need to apply some property of ReLU, you can finish your result. Here I put some remarks about some related work, like for this work, there's some work. This work deal with one-dimensional convolutional neural network. This kind of convolution is defined by polynomial multiplication. Actually, this step, the first and the third steps are easy to establish. The second step, the decomposition theory, is the key of this theorem. So if you have a convolution that is defined by polynomial multiplication, then if you have a large kernel in this convolution, then your decomposition theorem becomes a decomposition theorem for polynomial, right? So we know that, okay, for polynomial on 1D with real coefficient, we know we can decompose it. We can decompose it to some polynomial with just a linear or a power of linear or power of quadratic, right? So then we finish the proof. But we know that on 2D we do not have any like decomposition theory for 2D polynomials. So that's the reason why we can just like generalize this result to 2D with this kind of convolution. And so that's the reason why we needed such a pure algebraic and constructive proof for this for this mostly commonly used convolution operation. And for this result, they can this one can be applied. This one can be applied to the second one can be applied to 2D, but that can only be applied to some special, very special function class. Like the function should be like a invariant transformation invariant in some sense, and this can only be applied to periodic padding. And okay, one thing I want to mention is that for this result, if you have periodic padding, you will have a very concise and straightforward proof. But if you have a padding with constant padding, then proof becomes very subtle. You need to be very careful about the index. And then we try to generalize our result to CNN with some more popular architectures like ReSNet, pre-active ReSNet, and MGNet. So first is like, okay, actually this ReSNet and the pre-active ReSNet, I want to make a clarification here. That is, okay, these two neural network established by the same authors, okay? But here is distinguished, that is, this is ReSNet and the pre-active ReSNet, they just have a different place to put this activation function. This is, and this one is in a general setup, this one is more efficient, observed by the Lex paper from the same author of ReSNet. And in our, right, like the dynamic system viewpoint, we are actually thinking about this kind of ReSNet. Actually, I don't know, there's no name actually for this kind of ReSNet, because if we refer ReSNet, especially for computer science guys, they will say this is a ReSNet. But it seems that for mathematical guy, when we refer to ReSNet, it seems this one. Okay. Anyway, so we have such a this following structure of ReSNet, but here we needed to put a projection operator here, PL. This is also discussed in the original paper of ReSNet, because here we have BL and AL. If we change the dimension of channel, we have to put this one to fit the channel, okay? And then we have the following theorem. Here we consider that this P is given a priori because, Okay, because you can think about it here. If we will put this PL as 0, if we put this PL as 0, so this one will, you can drop this term, right? Then this will just degenerate to a classical CNN. Then, right? Then in some sense that is cheating, approved, right? So, and the other, the other important reason is that actually this identity in ReSNet is a key, is crucial feature of ReSNet. We needed to put this one and in priority, and we do not train this in some sense. So here to deal with that one, we needed to put some extra effort, but finally we can still prove this. Okay, and then for pre-active ReSNet, we still similar to the ReSNet, we still needed to given this projection in priority, and but we can still prove it. But here we needed two extra channel for the last output, such that we can actually we can deal with this effect of this term. Okay, and then we hope to deal with some ImageNet. First, we introduce ImageNet a little bit here because if you're familiar with multi-grid just we have just two main components for multi-grid. One is smoothing on each grid, and then along each grid you will have a restriction pooling in the CNN language or coarsening in multi-grid language, right? And we have this structure. If we get rid of this nonlinear activation, we got a pure geometric multi-grid. If we add this is ImageNet. Okay. And then we correspondingly we have ImageNet structure like this, and also this piece is given a priority. Actually, the reason why we are interested in pre-active ReSNet and we prove the approximation for it is that we can have a simple connection between the ImageNet and the pre-active ReSNet, and then we can prove the approximation result for ImageNet based on the approximation result for pre-active ReSNet. And finally, we have some concluding remarks. Okay, so here for this work, we actually the first thing is that we have a decomposition theory for convolution with large kernel on 2D. Okay, for constant padding or periodical padding. Okay, and then we have the approximation theory for the classical structure, and we have for some popular structure. And then we are thinking about some future works like because for this work we do not involve like a pooling. We want to incorporate pooling in approximation theory of CNN, and also maybe this can be applied to numerical PDEs. Or because here we needed to have a bridge that is DNN with one hidden layer. So we hope that we may have some more intrinsic approximation theory for CNNs. Thank you, everyone. You are welcome for questions.
Thanks a lot. Maybe we have time for one quick question.